Online viewers, welcome to our lecture video. In lecture video, we are going to do the analysis of this frame, which means we are going to find the axial force, shear force, and bending moment acting on this frame. I've already created many problems related to analysis of frame, which link you're going to find in the description box below. So right now we are going to talk about this problem. So as you can see here in this figure, we have two members, member AB and member BC, and there is for the member BC we have UVL of 10 kN per meter acting over a span of 6 meter, and for our member AB we have a UDL, uniformly distributed load, acting over a span of 4 meter. So we are going to do the analysis of this frame. So before doing the analysis of this frame, first and foremost we need to find the support reaction. So as you can see here, we have a roller support over joints, so we are going to have only one support reaction acting vertically upward, which is RCY, while we have a hinge support at A. So we are going to have two supports, vertical support and horizontal support. Horizontal support is denoted as RAX, and vertical support RAY. RAX and RAY being our X and Y direction. So our first and foremost step is going to find the magnitude of this support reaction. But before finding the magnitude of this support reactions, we need to know whether our frame is statical determinant or not. So firstly, we have number of unknown reactions. Number of unknown reactions is equal to 3, and as you know, we have three equation of equilibrium. Equation of equilibrium is also 3. We're going to denote this as R. We have three equations of equilibrium, which are EFX equals to 0, EFY equals to 0, and E moment equals to 0. So now we have R minus 3, which means 3. R is our 3, which is our number of unknown reactions, which is 3, minus our available equation of equilibrium. This three equations are 3. 3 minus 3 is 0. So our given frame is statically determinate. Statical determinant. So what does statical determinant mean? Statical determinant means we can find the value of these unknown reactions using our available equation of equilibrium. So which means we can find our value of RAX, RAY, and RCY. So our frame is statical determinant. So next we're going to find our values of RAX, RAY, and RCY. Is going to be our step first. So now for our step 1, we have our calculation of support reactions. Calculation of support reactions. So now we're going to find our value of RAX, RAY, and RCY. And while calculating our value of RAX, RAY, and RCY, we can follow any sign convention. We can take our clockwise moment as a positive, we can take our upward forces as positive, we can take our forces acting at right as positive, or we can take our anti-clockwise moment as positive, forces acting downward as positive, or force acting at left as positive. We don't need to follow any sort of specific sign convention while calculating our support reaction, but while calculating our shear force and bending moment, we need to follow our specific sign convention, which I will talk in the later part of the video. So first we are going to calculate our support reaction. So in order to calculate our first support reaction, we are going to take our moment. So right now I am taking clockwise moment as positive, and we are going to take our moment about A equals to 0. So as you can see here, since we have a hinge support at A, so there are not going to be any moment. But instead, let's see if we had a fixed support over here, we are going to have moment. But right now we have hinge support. Hinge support means just two reactions, vertical and horizontal, no moment. So no moment about A, which means E moment EMA equals to 0. So now we are going to get our moment about A, and our moment simply means force into distance, while our distance R is our perpendicular distance. Now to calculate moment about A, we need to see all the forces which are going to produce moment about A. So we need to follow a specific path. So one of the easiest way is follow a specific path. Move from A to C or move from C to A, so that you do not miss all the forces acting on A. So right now I'm going to move from C to A, and as you can see here, on the C I have RCY and RCY, and my distance of RCY from A is 6 meter. So I have RCY into 6. But RCY produces clockwise or anti-clockwise moment. So in order to know that, what you can simply do is you can just draw an imaginary line this way and shift RCY downward. So just to make your imagination easier, what you can do is you can shift your RCY downward, and right now point A is fixed, and this is my RCY. I'm shifted down, and as you can see here, with respect to A, RCY is going to produce your anti-clockwise moment. RCY is over here, and it pushes your beam upward, which means anti-clockwise moment. And right now I'm taking clockwise moment as positive, so anti-clockwise moment is going to be negative. plus. Now we need to see the force of 10 kilonewton per meter. We are going to see the moment it produces. So right now we have UVL, and in order to convert UVL into point load, what you can do is we are going to take the area of this triangle. As you can see here, it represents as a triangle. So right now, to convert our UVL, uniformly bearing load, into point load, what we are going to do is we are going to use our formula of triangle, area of triangle, which is 1 by 2 into base into height. So as you can see here, 1 by 2 into our base is 6 meter, our base is 6 meter, into our height is 10 kilonewton per meter, and this is equal to 30 kilonewton. 30 kilonewton. So the point load of this UVL is 30 kilonewton, and this 30 kilonewton will let me draw my figure this way. So now we have converted this into point load in this way of 10 kilonewton, and this 10 kilonewton will act at a distance of L by 3 and 2L by 3. L by 3 from its longer edge, from its longer edge it will act at a distance of L by 3, and from its shorter edge or from its ending side it will act at a distance of 2L by 3. So which means L by 3 means 6 by 3 is 2 meter, and 6 by 3 is 2 meter, and remaining is 4 meter. So it will act at a distance of 2 meter from its point B. From its point B, it will act at a distance of 2 meters. So right now, now we're going to calculate the moment of this as well. So now converting it acts at a distance of 10 kilonewton. So let me use the same concept as for C. Now for this UVL, let me shift that UVL downward with respect to point A, shifting it downward. As you can see here, if I shift it downward, it's going to act this way, 10 kilonewton. So just for your imagination portion, just to make your work easier, to understand how the movement will act. So as you can see here, 10 kilonewton is acting at a distance of 2 meters. So let me just write 10 into 2. But clockwise or anti-clockwise, as you can see here, 10 kilonewton is acting downward. So with respect to point, it's going to push your beam this way. Which means clockwise moment. It's going to push your beam with respect to A this way. So clockwise moment. 10 into 2. So now we have completed RCY, we have completed this UVL as well. Now we are going to go for our UDL. So now to convert our UDL into point load, what we are going to do is we are going to simply multiply our UDL over the span it is acting. So 6 into 4. So 6 into 4, we have 6 into 4, which means 24 kilonewton, and our UVL will always act over the half of its span. So right now, which is 4 meters, so it will act at a distance of 4 by 2. 6 by 4 into 4 by 2. So as you can see here, let me show it this way. This is our UVL, just of 6 kilonewton per meter. And in order to convert our UDL into our point load, what we simply need to do is we need to multiply over its span. We need to multiply the UDL with its span. So 6 into 4 is 24 kilonewton, and it always acts at midpoint, which means half of 4 is 2 meter and 2 meter. Now we need to see whether it produces clockwise movement or anti-clockwise movement about point A. So you know that what you can simply do is you can turn your figure this way, and by converting into point load, what you can see is about point A, this force is acting downward, and it is trying to rotate the beam in this way. As you can see here, fixing this beam, as you can see here, this force is acting downward. The force is acting this way. This way, the force is 24 kilonewton. And as you can see here, this force is pushing our beam downward. As you can see here, it's pushing this type of moment about point A. Point A is fixed, and 24 kilonewton is pushing our beam downward, which is our clockwise moment. So it's going to be positive. Plus 6 into 4 into 4 by 2 equals to 0. On solving this, we are going to get our value of RCY simply as 18 kilonewton. So this is our positive, which means upward. So right now we are following this sort of sign convention. You can follow this as well. You are not going to get any sort of different answer. Next we need to find our RAY, and after RAY and RAX, what we are going to take is we are going to take forces acting at right as positive. EFX equals to 0. Forces acting at right as positive, and now so let me see all the forces. We have RAX plus 6 into 4 is 24 equals to 0, which means I am going to get my value of RAX as minus 24 kilonewton, which means 24 kilonewton is acting at the direction of left. Now is next we are going to find EFY. So right now I am taking forces acting upward as positive. EFY equals to 0. So right now I have RAY plus RCY. So as you can see here, we have two forces acting upward, RAY, RCA, and this UVL as well. This is acting downward, so I'm going to take this as minus. So I converted my UVL into point load, and it was of 30 kilonewton right over here. Minus 30 equals to 0. So next I have RAY, I have my value of RCY as 18 minus 30 equals to 0. So now I'm going to get my value of RAY as 12 kilonewton. 12 kilonewton. So in this way we can find the support reaction. Why do you have done different as well is, right now I took moment about A, you could have taken moment about C as well. You could have done that as well. You can take your clockwise moment as positive and EMC equals to 0. So we have a roller support about C. So roller support also doesn't produce any sort of moment, so roller support so moment about C is also 0. So we have EMC equals to 0, and you can solve this as well. So let me write it down quickly. What you are going to get is, I'm going to go from A to C. So right now with respect to point C, RAY is going to produce your clockwise moment, so positive RAY into 6, and RAX with respect to point C, RAX is going to produce your anti-clockwise moment. If you shift the force over, and RAX is pushing the beam this way, which means anti-clockwise moment minus RAX into 4. And next we are going to see your this load 6 4 20. This load of this UDL is also going to produce about your point C. This UDL is also going to produce your anti-clockwise moment, which means minus 6 4 24 into 4 by 2 is 2. And for this finally, for this UVL is also going to produce your anti-clockwise moment, which is going to be minus 30 into 6. Minus 30 into 2 by 3 into 6, sorry, minus 3 into 2 by 3 into 6 equals to 0. On solving this, we are going to get 6 RAY minus 4 RAX minus 24 to the 48 minus 120 equals to 0. So 6 RAY minus 4 RAX equals to 168. So you can do this as well. So I'm just showing how you can take your moment about C. Why I multiplied by 2 by 3 is, as you can see here, about C, this is our shorter edge. As I explained before, our point load acts at a distance of 2L by 3, which is 2 into 6 by 3, which means 2 to the 4 meter, 2 into 6 by 3 from our shorten edge from our point C. From our point B it was longer edge, but from our point C it's a distance of 12 by 3. So I multiplied by 12 by 3. You can take moment about C, or you can take moment about A as well. I'm just showing how you could have taken moment about C. So after calculating our support reaction, now we need to find our axial force, shear force and bending moment for our each and every member. So now before jumping into calculating our shear force, bending moment, axial forces, so before that we are going to show all the forces acting on our beam. So let me just draw our portions AB and portion BC separately. So this is my portion AB, this is my portion BC. So now I calculated my value of RAY and RAX. So let me show that firstly. This is going to be my RAY. So I calculated my value of RAY as 12 kilonewton. This is my 12 kilonewton. So let me write it over here. 12 kilonewton, and RCY is 18 kilonewton. 12 and 18. So this is my 12 kilonewton, while my RCY is 18 kilonewton. This drawing the figure, this portion is very important in order to calculate our shear force and bending moment. So next I found my value of RAX as minus 24 kilonewton acting at our left, 24 kilonewton acting in this way. So now we'll write down all our remaining loaded as well. So I have my UDL over here, 6 kilonewton per minute, which is 24 kilonewton acting downward. Next is my UVL, and I have found my UVL magnitude to be equal to 30 kilonewton acting downward. 30 kilonewton. So right now we have to balance our forces as well. So as you can see here, 12 kilonewton is acting vertically upward. So in order to maintain equilibrium for our member member AB, a force of 12 kilonewton must act at our joint B. So at our joint B, a force of 12 kilonewton must act inward in order to maintain equilibrium, while we have a 24 kilonewton force acting upward and 24 kilonewton acting force downward. So no extra forces, so no any other forces will act at point B to maintain equilibrium. So next what we have is, we have a force of 12 kilonewton acting upward, 12 kilonewton acting downward. So in order to maintain equilibrium, what happens is, at our joint B we need to have a force of 12 kilonewton acting upward. So you can understand in this way as well. There is a force of 30 kilonewton acting downward, and there is a force of 18 kilonewton acting upward. So in order to maintain equilibrium, a force of 12 kN must act upward. So 18 plus 12 is 30. So you can understand it this way or in this way as well. A force of 12 kN is acting vertically upward at A. A force of 12 kN must act downward in order to maintain equilibrium. If there is no such force of 12 kN, the beam will move upward because of these forces. Similarly for our joint B as well, since there is a force of 12 kN acting downward, a force 12 kN must act upward, and this 12 kN will balance our force BC, will balance our member BC as well, because 30 kN downward, 12 plus 13 is 13, 30 upward, 30 downward, so our beam BC is also now in equilibrium. So right now we haven't added all the forces acting. We have to add some more forces which will add later on when we calculate all those values, and we'll update our figure accordingly. So now we'll look out for our member AB. So now as you can see here, our overall frame is in equilibrium. Since our overall frame is in equilibrium, what we can see is our member AB and member BC are also in equilibrium. If our member AB and BC are not in equilibrium, then our overall frame is not going to be in equilibrium. So we are going to use that concept, and we are going to take our member AB first of all, and we are going to consider our member AB in equilibrium. So firstly, what we are going to do for our step 2 is now we have moving towards our step 2. So now step 2, what we are going to do is we are going to consider equilibrium of member AB. Consider equilibrium of member AB. So let me draw my member AB over here. This is my member AB. There is a force of 12 kN acting upward, and there is a force of 24 kN. This is my joint B, and this is a force of 12 kN downward. 12 kN acting downward. So I have simply drawn this figure one more time over here. So now what we are going to do is we are going to firstly find out our axial forces. So what are axial force? Axial force are simply those forces which act along our member. Just joint A. So as you can see here, along our member AB, there is a force of 12 kN acting along our member AB. So simply our axial force means those forces which act along our member or parallel to our member, whatever you can say. So 12 kN is acting along our member AB. So this is going to be our axial force. So firstly we are going to find our axial force. Axial force and AB equals to 12 kN. So now as you can see here, this 12 kN is compressive of nature, or as you can see here, if this is our member AB, 12 kN both are pushing our beam inward. They are pushing our beam inward, which means it is producing compression. For our compression, we are going to take our sign as negative compression. Next is our shear force. So what are shear force? Shear force are simply those forces which act perpendicular to our member, which act perpendicular to the direction of our member. As you can see here, we have a force of 24 kN acting perpendicular to our member. So in order to calculate our shear force, we can do two ways. We can either take a section, certain section x1, x1. You can either take a section, or you can calculate it directly as well. So I'm going to do both in order to make you understand clearly. Let me do it in both ways. So firstly, while taking a certain section x1, what I need to be careful is where to take our section. We need to take our section x1 in such a way, or at a such a length it incorporates, or it takes up much of the forces acting on it. So as you can see here, right now I have taken my x1 right of 24 kN, but if I had taken my section x1 left 24 kN, it do not include our force of 24 kN. So in order to include our maximum number of forces, we are going to take our section x1 right of 24 kN. So right now I am taking my section over here. Hope you have understood where to take our section. Take your section at that point at which it will include your maximum number of forces. So right now I am taking my shear force at over here. So shear force at x1. So before at the first of the video, I told that while calculating our support reaction, you could have taken any sign convention. But as I said before, you need to follow a certain sign convention while calculating your shear force and bending moment. And that sign convention is, while moving from left to right, we are going to take our upward forces as positive, while our downward forces are going to be negative. While moving from left to right, our upward forces are going to be positive. upward forces are going to be positive and downward forces are going to be negative. While we are moving from right to left, it is just going to be vice versa, upward force negative and downward force positive. Similarly for your movement as well, while moving from left to right, we are going to take your clockwise movement as positive while your anti-clockwise movement as negative, and vice versa while moving from right to left. So we are going to follow this sort of sign convention. And right now we are moving from right to left, we are moving from point A or joint A to joint B. So we are going to follow this sort of sign convention. So as you can see, let me turn this figure this way. So as you can see, while moving from A to B, I have my 24 kilonewton acting particularly upward. Particularly upward means positive, so plus 24 kilonewton, plus 24 kilonewton, minus, so you can simply says 24 minus. So right now what I have is, I have so I have not shown it over here, but initially in my question what I had a UDL, uniform distributed load of 6 kilonewton per meter, and this is at a distance of x1. So let me show my UDL as well. There is a UDL. So UDL, the UDL value is 6 kilonewton per meter, 6 kilonewton per meter. So as I explained before, in order to convert UDL into point load, we need to multiply the value of UDL over its span, with which it is acting. So right now 6 kilonewton per meter is acting over a span of x1 for over x1 for our section x1. So we're going to multiply 6 into x1. It's going to be our shear force at section x1. So y minus, so as you can see, as I explained before, while moving from left to right, upward force are negative while our downward force are negative. So downward force are negative. So as you can see here, this UDL is acting vertically downward, so minus 6 its magnitude over its span x1. Hope you have understood why I have done minus 6 into x1, because it is acting vertically downward and it is acting over a span of x1 meter. So next what we are going to do is, now we are going to vary our x. So when x1 equals to 0, shear force at A equals 24 kilonewton. When x1 equals to, we are going to take this is a total of span of this is the total span of 4 meters. So we are going to take next point at 2 meter. 2 meter equals to 6 to the 12, which means 12 kilonewton. While our x1 equals to 4 meter, which means we have reached our point B, so our 0 kilonewton. You could have done this by taking our section, or you can simply do without taking your section as well. You can take your shear force at A equals to, as you can see here, shear force at A over at point A. What we have is, we have a 24 kilonewton acting vertically upward. So as I explained before, left to right, upward force positive, which means 24 kilonewton. Next we have at point 2 meter. At 2 meter, as you reach the point of 2 meter, you have your UDL. You have your UDL acting vertically downward, which means 24 minus 6 into 2, which is 12 kilonewton only. We have 6 kilonewton, but right now we are taking a span of 2 meters, so 6 into 2, UDL is downward, so negative. So now finally at our point B, we are going to get our 20. We are going to get, so on up to point 2 we got 12 kilonewton, and finally when you move to our point D, we are going to get 12 minus 6 into 2 again, which means 0 kilonewton. Why this? Because we have right now moved up to point B. Now as we move to our point C, which means right now we are 12 kilonewton, and as we move to our points, there is remaining UDL. There is remaining UDL of 6 into 2, 6 into over a span of 2 meter. So 6 into 2. So this is simply the same as this one. We can do any of this, whichever you find easy. Next, what we need to do is, after calculating our shear force, we need to find, for our number third, we need to find our bending moment. So while calculating our bending moment, we can do the same, whether you can take your section x1, or you can calculate directly as well. So right now I'm going to do it by using our section x1. So right now we are at a point A. So with reference to x1, what you can see is, with reference to point x1, I have kept my pin over our section x1. With reference to this, 24 kilonewton is producing your clockwise movement. As you can see, 24 kilonewton is pushing upward, which means it's producing a clockwise movement, and it's acting at a distance of x1. So 24 into x1. But as I explained before, while moving from left to right, clockwise movement is positive. So right now it's going to be my positive direction. Next, what we have is I need to incorporate my UDL. As you can see here, with reference to this point, UDL is acting downward, and is producing your anti-clockwise movement. Downward means anti-clockwise movement, so we are going to take it as negative. So this is going to be minus, my magnitude is 6, it is acting over span of x1, and as I explained before, UDL will always at a distance of x1 by 2. 6 is my magnitude, x is my over the span. So I multiplying by this, I converted my UDL into point load, UDL into point load, and it will always at a distance of half of its span, which means x1 by x2. So right now this force is acting in this way, x1 by 2. Hope you have understood how this is calculated. This is going to be 24x1 minus 2 3 6 3x1 square. So let me show it this way. This is my section x1. This is my distance x1. My 24 kilonewton is over here. This is my 6 kilonewton per meter. In order to convert this 6 kilonewton per meter into UDL, what I'm going to do is I'm going to multiply this 6 kilonewton per meter by the span. It is acting at a span of x1. So this is what I did. 6 into x1 came over here. And now for the remaining distance, this is my point load, and this point load will always at a distance of half of my span, which is x1 by 2. This is x1, so it will always at a distance of x1 by 2 from this section x1. So simply x1 by 2. So I got 24x1 minus 3x1 square. So next what I'm going to do is I'm going to do the same. So now I'm going to take my distance of when x1 equals to 0, moment about A will be 20 will be 0. So if you put 0, we're going to get 0. When x1 equals to 2 meter, I'm going to get my moment about 2 meter, which is going to be equal to 36 kilonewton per meter. And if I take my x1 as 4 meter, I'm going to get my moment about B, which is going to be value. I'm going to get this value as 14 kilonewton per meter. So now after doing this, we have I have got my moment about B. So now I need to update my figure. So this is a really important part. So right now I got my moment about B as 48 kilonewton per meter, and this is my positive moment, which is my positive or clockwise moment. So about B, I need to show 48 kilonewton meter. Now we have calculated our moment about B as 48 kilonewton per meter. I calculated it as 40 kilonewton per meter, and I need to show it over my AV, and I need to show my 14 kilonewton per meter. 48 kilonewton per meter. 14 kilonewton per meter. So now let me explain about the sign, why I have taken my sign in this way. So this is my member AB. Right now I'm going to take my member AB over here. So right now for our member AB, I'm going to have two types of moment: sagging bending moment and hogging bending moment. So what are sagging bending moment and hogging bending moment? So let me draw my beam this way. So if the beam moves downward in this way, I'm going to take this as sagging bending moment. So it will be my sagging bending moment if the beam moves downward. But if the beam moves upward in this way, I'm going to take this as hogging bending moment. This is my hogging bending moment. This is my sagging bending moment, and this is going to be my hogging bending moment. So for my sagging bending moment, I'm going to take it as positive, while I'm going to taking my hogging bending moment as negative. And for my sagging bending moment, I'm going to have my moment about left as I'm going to have moment in this way. I'm going to have moment in this way. But for my hogging bending moment, I'm going to have moment in this way. Moment in this way. So as you can see, this beam is moving in this way. It's trying to move upward. So moment will act in this way. So let me explain why moment acts in this way as well. Since I am explaining all the topic clear by clear, step by step, so let me explain this as well. So if you like our video till now and if you're understanding all the concept, do subscribe our channel. It will mean a lot. So let me explain why moment is acting upward. So as you can see here, let's say this is my beam. This beam is moving upward. So as you can see, there is a tension over here and there is compression over here. Since moment is a reaction force, it always acts opposite. Where our force is applied. So our maximum force, as you can see here, our crack can appear at over here in this lower portion. As you can see, there is expansion, or this portion is expanding in this way. So if I take my scale and if I move it downward, you can experience that the downward is the scale is expanding downward, or the beam is expanding downward. So movement, which means our opposite reaction will act upward, while it is our vice versa for our hogging. So as I explained before, we're going to take our sagging as positive, and we're going to take our hogging as negative. So what I obtained over here is I obtained 48 kilonewton per meter, which is positive, which means it is sagging. So what is my sign for sagging is, it is going to be this way. It is going to be clockwise at this is my left, this is my right. It's going to be clockwise at A. So this is my portion A. It's going to be my B. It is going to be clockwise at A and anti-clockwise at B. So as you can see here, for my member AB, I need to put on my anti-clockwise sign. So hope you have understood why I have put anti-clockwise sign. This is because of my sagging bending moment, and for my sagging bending moment at right, I'm going to have clockwise moment. Hope you have understood why moment, why the sign of moment and how the sign of moment has been kept over here. If you still have any queries, we can comment down below. I'll clearly explain you there. So next, what I have done is we have drawn our 40 kN per meter. So our next important step is what we need to do is what you need to do, what you need to understand is joint transfer moment. Joint transfer moment. This is our very important point. Joint transfer moment. So for our joint A, we have 48 kN per meter. So for our joint BC as well, we are going to have a 48 kN per meter. So we are going to have this way, this sign 48 kN per meter. So as I explained before, why the sign is upward. Hope you have understood why. Because 48 kN per meter, it get transferred for our member BC as well, and this is our sagging bending moment. So sagging bending moment, the sign for our sagging bending moment is clockwise. Clockwise for our side A, for our left side is going to be clockwise moment. So 48 kN per meter is acting, particularly is acting in a clockwise direction. So now we are going to solve for our member BC. Hope you understood till over here. If you haven't, you can clearly comment down below. I'll answer you there. So now we are going to consider our equilibrium of member BC. So like for our AB, we are going to calculate our axial force, shear force, and bending moments respectively. So let me write down consider equilibrium of member BC. Consider equilibrium of member BC, and we are going to draw out our every forces acting over here. So this is my member BC. This is my member BC, and there is so right now I'm not going to draw this figure. I'm going to draw my initial figure. It will be a little bit easier. It will be a little bit easier then. So this is my initial figure for member BC. So let me draw this only. There is my UVL of 10 kN per meter. This is my 10 kN per meter, and I have a certain moment about B in this direction, not this. In this direction, I have my moment of 48 kN per meter. As you can see over here, 48 kN per meter, 48 kN meter, and for my C, I have 18 kN. These are all my forces acting over here. So right now, first I'm going to calculate my axial forces. So as you can see here, as I explained before, axial forces are those forces act along our member BC, but there are no such force acting along our member BC. As you can see, there are no force acting along BC or parallel to BC. So we are simply going to write this as axial force and BC equals to 0. Axial force and BC equals to 0. Next, we are going to calculate our shear force, and while calculating our shear force, we are going to shear force at x2. We are going to take a certain section at x2. So before doing this, let me write down my span as well. This is acting at a span of 6 meter. So let me explain one important point regarding your UVL. One of the most important part of our UVL is while calculating our UVL, we are always going to move from our shorter side to our longer side. We're not going to move from our longer side short side. We're always going to move while calculating our shear force bending moment. While dealing with UVL, we're always going to move from our right to left. I'll explain why that as well. So we're going to take a certain section x2. This is my certain section x2, and it is at a distance of it is at a distance of x2, and it is at a distance of x2 from my side C. So let me explain now. Let me calculate the magnitude of. So we have a certain force acting over here. Let me calculate this as Wx. So as you can see here, now we have taken a certain section, and this we have a certain UVL. We have certain UVL, and for certain and for section x2 as well, we are going to have certain UVL. And now I'm right now, as you can see here, I'm going to take this much portion as well. So I need to find the magnitude at this point. I need to find the magnitude of UVL at this point, and I have suppose that magnitude as Wx. Now next, what I'm going to do is I'm going to use my concept of similar triangle. So let me since now I'm going to take my small triangle. As you can see, this small triangle has this length as Wx, and it has my smaller length as x2 divided by x2 equals to my bigger length. This corresponding bigger length is 10 divided by this corresponding length is 6. Hope you have understood why I have taken Wx. So right now I'm going to deal with small section of x2. So I need to find the magnitude over here. So I suppose this magnitude as Wx, span is x2, while its corresponding bigger side is 10, and the length is 6, 10 by 6. So this is going to be Wx equals to 2 5s are 10, 2 3s are 6, 5 by 3 x2. So the force or the magnitude of UVL at this point is 5 by 3 x2. So now, as I explained before, we are going to take our shear force from right to left. So as I explained before, for our sign convention, while we are moving from left to right, we are going to take our upward force as positive and downward force as negative. So it's going to be vice versa for right to left. While moving from right to left, we are going to take our upward force are positive and downward force are negative. So while we are moving from right to left, we are going to take our upward forces as negative, and downward forces will be positive. Exactly vice versa while moving from right to left. So if you have understood the sign convention for left to right, it is going to be exactly vice versa. So we are going to move from our C to B. So let me write down my shear force. So my shear force is going to be, as you can see here, I am moving from C to till our section x to x2. Don't look at this portion, we are not going to deal with this portion, we are going to deal with our portion up to x2 only. So we are going to see up to here only. So from C to x2, I have my 18 kilonewton acting upward. So as I explained before, upward force are negative, so I am going to write it as minus 18 plus, let me write on plus. So next what is my forces? I am to deal with my force wx. So now wx is my UVL. This is my value of UVL. So I need to convert my wx into my UDL. So as I explained before, in order to convert my UVL into UDL, I am going to use my area of triangle formula, which is 1 by 2 into base. My base is x2. This wx is acting over span of x2 into wx into wx into my shear force minus 18 plus 1 by 2 into x2 into wx. So why I'm taking so this is going to be positive, and this is going to be positive because while moving from right to left, downward force are positive, so it's going to be positive. So this is my shear force. Now we are going to let me write down one more line. Minus 18 plus 1 by 2 into x2 into my value of wx is 5 by 3 x2. This is going to be minus 18 plus 5 by 6 x2 square. So let me now, I'm going to change my value of x2 to calculate my shear force. When x2 equals to 0 meter, I'm going to get x2 0 means I am now at point C. BC equals to minus 15 Newton. So now when x2 equals to 3 meter, my span is 6. We're going to take another point at half of the span, which means 3 meter. I'm going to get V 3 meter equals to minus 18 plus 5 by 6 into 3 square. It's going to be my value of minus 10.5 Newton. Now finally for our point B, which means x2 equals to 6 meter, I reach my point B. This is going to be 0 kilonewton. So it's going to be 12 kilonewton. 12 kilonewton. And as you can see over here, in order to check whether I have done this right or wrong, I found my shear force. I found a vertical force of 12 kilonewton at B, and this is acting upward. So acting upward. So right now I got my positive value of 12 kilonewton. So right now I am moving from right to left. So I got positive value. This means the 12 kilonewton is acting downward at point B. So this point B is actually at right of it. Just a point right of it, which means it could be at 5.99999 meters, something like that. I have got my value of 12 kilonewton, but as I move beyond of B, at left of B, I am going to get my value of let me write down this way. BB left will be simply equal to 12 minus 12, which means 0 kilonewton. Why this? Because I already have a force acting vertically upward at 12, and right now I got my force acting vertically downward. Need to show this at your picture. I'm just trying to explain you how I have got my correct value, because shear force at joint must be 0. So as you can see here, I got 12 and 12, which means 0. 12 minus 12 is 0. So as you can see here, in this way we can check your answer as well. Now next we are going to calculate our bending moment. So now in order to calculate our bending moment, we are going to take our shortened section x2. We are going to take our bending moment over x2, and let me write down my general equation in this case as well. So right now I have my 18x2, and 18x2 with reference to x2, it is acting vertically upward, and it's producing anti-clockwise moment. So let me write down a sign convention as well. While moving from left to right, I had my clockwise moment as positive, while my anti-clockwise negative movement as negative. While moving from right to left, it is going to be exactly vice versa. Clockwise movement will be negative, while my anti-clockwise movement will be positive. So right now we are moving from right to left, and now I have my 18 kilonewton producing your anti-clockwise movement. So I'm going to take it as positive 18 into x2. Now it's a little bit confusing part. Now for our UVL, we have wx. Now we converted this into our point load. Now converting, let me draw this figure so it becomes much more clear. So this is my section x2. This is my section x2. Do not look over this portion. Right now we are going to talk about our section x2 only. This is my section x2. Now I convert it into point load. I converted my UVL acting over this region into point load, and I'm going to get my value as, I'm going to get this value as 1 by 2 into wx into x2. As I explained why, because right now I'm using my in order to convert my UVL into my point load, I'm going to use my formula of area of triangle 1 by 2 into base into height. So you have understood this y, and this will add at a distance of 1 by 3 x2 from its longer edge and 2 by 3 x2 from its shorter edge. So I have already explained this before as well. So right now, in order to calculate moment about x2, 1 by 2 wx into x2, this point, this UVL is acting downward, which means it's producing a clockwise moment. It is acting this way, clockwise moment. So what is clockwise moment? Negative. So now we're going to minus 1 by 2 into wx into x2. So this is my magnitude of load, and it's at a distance of x2 by 3 into, from with reference to point x2, it is acting at a distance of x2 by 3. Meaning you can get confused regarding your distance, so you need to be really careful how it got 1 by 3 x2, where right now we are talking about section x2. So wx is also our point load is right now at a distance of 1 by 3 x2 from our section x2. So simply we are going to do x2 by 3. So 18 x2 minus 1 by 2 into value of wx is 5 by 3 x2 into x2 square by 3. It's going to be 18 x2 minus 5 by 339 to 18 x2 cube. So this is going to be my general equation to calculate my bending moment. So I'm going to value my x2. So when x2 equals to 0 meter, I'm going to get my moment about c, which is 18 kilonewton per meter. Sorry, it's going to be 0 kilonewton per meter. 0, we put 0, 18 into 0 minus 5 18 into 0 0. When x2 equals to 3 meter, I'm going to get moment about 3 meter, which is going to be equal to 46.5 kilonewton per meter. And finally, when x2 equals to 6 meter, I'm going to get moment about b. Actually, I have already calculated my moment about b, and I found that to be 40 kilonewton per meter. I will explain this before. So as you can see here, I get the same value on putting 6. I'm going to get 48 kilonewton per meter. So as you can see here, my value is correct. So as you can see here, you can check your answer as well in this way. So now after completing all this, now we have to draw our axial force diagram, shear force diagram, and bending moment diagram. So now we're going to draw our axial force, shear force, and bending moment diagram. And so let me first draw my axial force. So I'm going to draw my member AB and member BC. This is my member A, member B, and member C. And if you remember, I found my axial force about AB as minus 12 kilonewton compression. So I'm going to denote it this way. I'm going to denote my minus downward, minus 12 kilonewton. So going to be minus, and this is going to be 12 kilonewton. And this is my axial force diagram, AFD. So while for our moment BC, I did not found any axial force. The axial force was 0, so you don't need to put any axial force. Now we're going to show our shear force diagram. Again, draw the same AB, BC, A, B, C. So let's see for our shear force about A. We found a bending moment about A as 24 kilonewton, and it ended 12 at 2 and 0. 24, 12, and 0. So about A it was 24. So I'm going to show positive upward 24, and it ended at 0, and it was 12 kilonewton. It was 12 kilonewton at a distance of 2 meters. So we're going to show that as well. This is going to be 12 kilonewton, and this is going to be 24 kilonewton. It's going to be positive. Now for our member BC as well. So for our member BC, we found our shear force about B as 12, minus 10.5, and minus 18. So minus 18 is about C. So about B is 12. 12 means positive. So we're going to show it upward, 12 kilonewton upward. And then as you can see over here, you can guess the nature of your curve in this way as well. We have x square. So for our UVL, it is going to decrease. It is going to decrease parabolically. We have x square. You can get that concept from here as well. You can get the nature of your graph from nature of your curve from this way as well. Minus 10.5, 12. So we are going to so about our B, we have minus 18. So let me show my minus 18. It's going to be 18 kilonewton, and we are just going to join this way. This way, it's going to be it's going to be positive. It's going to be negative. So our shear force is also shear force diagram. SFD is also shear force diagram. SFD is also completed, and we had a minus 10.5 somewhere in the middle. It was from B minus 3 point minus 10.5. You can show it over here as well. You can show it in this way as well. Minus 10.5 kilonewton. We cannot show this as well. It's going to be a simply shear force diagram. Next we have our final is our bending moment diagram. So we're going to draw our side member A, member B, member C, and for our member AB, So for our member AB, we found our moment as 0.3648. So we're going to show that 0.3648, and and for our bending moment, we are going to show our positive downward. So it is the same concept of our sagging and hogging, as I explained before. Sagging, which means downward, is positive. So which means if our beam moves downward, it is positive. So with that concept only, we are going to show our bending moment downward, because positive means sagging. Our beam is moving downward. Same the concept, using the concept of sagging and hogging, we are going to show our bending moment downward. So we have our bending moment as 0.3648. So we are going to have again our parabolic. We have our UDL, which means our bending moment is going to vary parabolically. So let me show it in this way. So this point is going to be 48, and somewhere in the middle we are going to have 36. So simply in this way, in the middle we are going to have 36 kilonewton per meter, while for our point B we have positive 30 unit, and so going to be 40 kilonewton per meter. Now finally for our BC portion, we have our bending moment as 0, 46.5 and 48. So it's also going to be positive. So positive means downward, sagging. So we're going to show this as positive downward. So let me put on my value: 48, 46.48, 46.5 and 0. 48, we're going to increase. We're going to start from 48 kilonewton per meter, and then we're going to move little bit upward to 46.5 and final to 0. 46.5 to 0. So as you can see here, we have a cubic function over. So our function is going to vary cubically. So you don't need to put much effort into your graph, but just to prove it, just draw straight, just draw cubically or parabolic in this way. 48, and in somewhere in the middle we have our value of 46.5 kilonewton per meter, and finally we have 0. This is going to be positive as well. Bending moment diagram. So in this way you can do analysis of frame. You can calculate your shear force, bending moment, axial force, and complete your analysis of frame. Hope you have understood how this has been done, and hope your concept is. Any queries, you can comment down below, and if you like our content, do subscribe to the channel and like our video. Thank you.